So today I'm going to start a new topic called analog meters, where we are going to discuss the moving mechanism of different type of analog meters and how the construction of those moving mechanisms are, and how they are implemented in constructing different types of uh, analog meters for electrical measurements, such as ammeters, voltmeters, or wattmeters, that we're going to cover in this portion of the discussion. So the first of all, I'm going to discuss about permanent magnet moving coil meters, or the permanent magnet moving coil mechanism, which is used for the uh, moving mechanism of the pointer. So as per the name suggests, that permanent magnet moving coil. So this type of moving coil arrangement or mechanism has two portions, like you have for the DC motor, stator portion and then rotor portion. Like here also you have a static portion in the form of a permanent magnet, and you have a moving coil that is going to result in the movement of the pointer of an analog meter. So as you can see in this figure, a horseshoe magnet is shown over here. So one side of the magnet is having a north pole, the other side is having a south pole. So the magnetic field lines are supposed to be going from north to south. And in between that magnetic field, a coil is placed, a coil arrangement is there that is able to rotate freely. So whenever this coil is supplied with some DC source, as shown over here, if this switch is closed, the coil is going to carry some current, and as the coil is carrying some current in the presence of a magnetic field, it is supposed to experience some force, which will eventually result in a torque, causing the coil to deflect. Now, the direction of deflection will depend upon the direction of current flow, the direction of the magnetic field, and accordingly, the deflection will take place either in the anti-clockwise direction or in the clockwise direction. For example, let's say here the coil winding is done in such a way that the direction of current is such that it will have an anti-clockwise deflection, as indicated over here. So let us focus on the arrangement of the coil, how the coil arrangement is done in general in case of this sort of moving mechanisms. So normally an aluminum frame is used. Around the aluminum frame, the winding of the coil is placed. So the number of turns of the coil is uh, uh, done around that aluminum frame. So this aluminum frame is containing the windings of the coil, and at the same time it is connected with the shaft and the pivot, and with respect to this point the whole coil arrangement can move uh, with respect to this pivotal point. So it can be said that this is the this is in I mean signifying the rotational axis for this particular coil arrangement, and in terms with respect to this rotational axis, the coil will have a circular trajectory. Now, in order to make sure that the movement is as smooth as possible, or as less friction it encounters, so some sort of bearing arrangement should be there, and oftentimes a bearing arrangement called jewel bearing is used, where the pointer of the pivot is inserted into the bearing arrangement so that the movement becomes as frictionless as possible. Now, along with the coil arrangement, two other uh, uh, parts has to be introduced. One is that on both sides of the shaft, some spring needs to be attached. Now, the necessity of attaching the springs is to generate some controlling torque or some opposing torque uh, to the main deflecting torque. So when the coil is carrying some current in presence of the magnetic field, it is going to experience some force, and the resulting torque will cause it to deflect. So this deflecting torque is going to deflect the coil in a particular direction. Now the task of the springs would be to provide an opposing torque. So that torque would be against the deflecting torque. So the deflecting torque has to work against the controlling torque produced by the springs to uh, obtain a certain amount of deflection. And the purpose of introducing this opposing torque through springs is to bring back the pointer into its initial position once the current supply is taken off from the coil. So like the voltmeters or ammeters we use in our uh, uh, electrical measurements, after we finish our taking the reading, if we turn off the supply, the pointer obviously moves back to the zero indicator again. So some mechanism should be there that brings back the pointer to the initial position. So this sort of spring mechanism can be useful in providing the necessary tension to bring the pointer or the coil back to its initial position. And in order to uh, take meaningful readings from the movement of the coil should be associated with the pointer. So a pointer should be attached with the shaft of the coil arrangement or the frame, so that when the coil moves, the pointer also moves. And the tip of the pointer should be placed in a calibrated scale, and the scale would be calibrated in terms of amperes if it is a ammeter, in terms of volts if it's a voltmeter, in terms of watt if it is an wattmeter. So it depends on which quantity or which type of meter needs to be constructed using this sort of moving mechanism. So with respect to that, the pointer has to be associated with a scale from where the observer or the user can take some reading. So this last figure actually shows sort of a complete coil arrangement for this sort of moving mechanism. Now, another thing to mention over here that for this particular figure, inside the aluminum frame, the whole space is empty. So there is nothing inside the frame. So this portion is actually empty. So sometimes in order to increase the magnetic permeability so that more magnetic fields can be concentrated easily inside this hollow uh, frame, some iron core is inserted to increase the magnetic permeability so that magnetism can be uh, 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 induced easily, like shown in this figure. So let's say this is the permanent magnet. Inside it there is the coil arrangement. So here a singleton coil is shown. Now inside the hollow portion of the coil arrangement, and a stationary iron core is placed. Also in this figure, the iron core is shown over here. So that is to increase the concentration level of the magnetic fields. Now if we talk a little bit more about the permanent magnet, so you can see that the pole faces are actually having a curved shape. So instead of having flat pole faces, the pole faces are curved a little bit. So if we consider a flat pole face, we have north pole one side, south pole on another side. So ideally, it is considered that the magnetic field lines travel in straight lines from one end to another, and they are considered to be parallel lines. So if flat pole faces are considered, then what would happen that the magnetic field lines will not cut the coils perpendicularly each time. Let's say if this is the coil arrangement, at this point the this magnetic field line is cutting the coil perpendicularly. So at that point, the developed torque is supposed to be maximum, let's say. But when the coil starts rotating, let's say it obtains this position. Now the magnetic field lines that are cutting the coil are not at 90 degrees or perpendicular to the edges of the uh, coil. So rather they are now at an angle. So the amount of torque development will also change, because the torque is normally defined as Fr into sine theta. So as the theta varies from 90 degree, so the amount of torque developed will also vary. So in order to decrease this possibility, the curved pole faces are used, because if a curved pole faces are considered, then the magnetic field lines can be drawn in this manner. Let's say from, if this is the north, this is the south pole. So from north to south, this could be one line, this could be another. Now they are not uh, uh, like the parallel straight lines in case of flat pole faces. Rather, they are having different angles. So
Sir,
when
I have a question.
yes.
Sir, from electromagnetic theory, we know that the magnetic line fluxes they don't cross each other. So how are they crossing each other here?
Well, this is a sort of an uh, uh, for the card pole faces actually. So they're supposed to be traveling from one end to another in terms of normally they are considered to be straight lines. Now, if they are not entirely touching each other, maybe there might be some uh, deviation from what I'm drawing over here. But for this case, it is sort of considered to be an uh, ideal scenario that what might happen. But one way or another, the flux lines are supposed to reach from one side of the North Pole to the other side of the South Pole. So that is the general convention that is normally used. Now, if this sort of an hypothetical scenario is considered, then for the coil arrangement, you can say that uh, for the coil arrangement when it is moving at different angles, or it is taking place at different angles, the field lines are almost going to be perpendicular to uh, perpendicular to the edges. I mean, even if it is not entirely perpendicular, but it would be close to uh, almost 90-degree angles when
Again,
the
sir, one more question.
yeah.
Sir, when the flux lines are changing medium, they should deviate from it, from their original path, like light. So they should not be straight in the iron core inserted inside the coil.
Well, those are practical scenarios, right? So if practical scenarios are considered, then obviously several effects come into consideration. But while some theoretical discussions are uh, conducted, normally for ease of analysis, some idealistic scenario is considered so that it is easy to uh, establish a hypothesis regarding a certain phenomena, like even doing analysis with a circuit that is consisting of a diode, let's say. So we know what to expect from the diode in a real world or practical scenario. But often for ease of analysis, we consider the diode to be working as an ideal switch so that it becomes easy to analyze the particular arrangement or a particular circuit. So in that sense, normally also dealing with the magnetic phenomena, normally for ease of analysis, the straight lines are considered. Okay, but obviously in practical case, they are not going to be as ideal as it is considered in case of theoretical analysis.
Okay, sir.
Now, the thing that to try to keep the field lines as much perpendicular to the edges of the coils as possible, that is due to the fact that we don't want the torque to be changing too much or deviating when the coil is rotating inside the magnetic field. So the pointer movement, that should have a smooth movement. So when it is rotating from its initial position, it doesn't the speed of rotation doesn't change too much. So if that is the case, if that can be ensured, then the scale can be calibrated uh, in a uh, in terms of an uniform scale. So where the different markings are placed at uniform distance. So rather than using a non-linear scale, a linear scale can be used in order to specify the different uh, uh, quantities in terms of, let's say, the amperes of voltages in those units. It can be a uniform scale can be formed. Now, this sort of moving coil mechanism is often referred as d'Arsonval movement because this scientist was the first one to uh, use this sort of moving mechanism in constructing electrical measuring devices. So after his name, this sort of moving mechanism is sometime or oftentimes is referred to as the Arsonval movement.
Sir, I have a question.
Yes,
If we consider the same principle and suppose that 2 meters are using the same principle of PMMC and 1 meter is able to measure in milliampere and another is microampere. So how do we relate the sensitivity to this principle? Like both are using the same principle, so one is more sensitive, another is less sensitive.
the sensitivity for this type of meters is normally defined by the maximum amount of current that a particular coil arrangement can handle. So, uh, after you construct a particular coil arrangement, definitely that coil arrangement has is supposed to have a fixed resistance and a fixed amount of current handling capability. So, how much current that coil arrangement can handle, that is often referred to as full scale deflection current. So that is actually a measure of the sensitivity of this sort of moving mechanism. If a small amount of current is sufficient for a coil arrangement to give the full scale deflection, then you can say that that meter is very sensitive because it can detect small amount of currents and give full scale deflection. Then using that meter, maybe you can, or that coil, you can try to form an ammeter that can measure in lower ranges, let's say in microampere ranges. And if you have another coil arrangement, maybe increasing the number of turns, or by some means you increase or the full scale deflection current increases. So more amount of current is necessary to give the full scale deflection. So those meters are normally uh, where the full scale deflection current is increasing. They actually give more, they require more current to give the full scale deflection. So in those cases, the sensitivity can be considered to be a little bit less, and those devices, those mechanisms can be used in case of measuring in the milliampere range or the ampere ranges. So it depends on the coil arrangement, because once you form a particular coil arrangement, as you have to construct it physically, you have it is supposed to have a fixed amount of current handling capability, or a rated current and a rated resistance. So it depends on that. So a little bit more about it might be discussed while discussing the DC ammeters or DC voltmeters later on.
And sir, we are using aluminum frame and then using some iron cores. So my question is, why aren't we using the iron frame at the first time? So basically, why we are using aluminum frame?
Well, uh, for that, I don't have an exact answer to that particular question, that why that is done. Maybe it's due to the durability. It might happen, or maybe to, uh, uh, I mean, uh, maybe iron is more prone to corrosion, whereas if the frame is made of aluminum, it might uh, give you a, let's say, less possibility of affecting the coil arrangements in uh, uh, protecting the coil arrangement from possible corrosion. And also maybe aluminum frames are lightweight, because let's say the iron core is static. So the iron core is not moving, but only the frame along the iron core that is moving. So maybe the aluminum frames, they have less weight if compared to iron frames. So if the weight of the frame is less, maybe the movement will be smoother. So those could be some possible reason, but I don't uh, uh, know the exact reason at this moment. So don't consider my answers to be 100% perfect, but this could be some possible reasons why, instead of making the entire frame using iron core, the frame is made of aluminum. And if the entire frame is have attached with the iron core, then what will happen when the coil arrangement is moving? The iron core will also move along with it. So the iron core is kept static, and around the iron core, the frame is not completely attached with it. Rather, it would move independently, and the iron core will remain static. So if the iron core was completely attached with the frame, the weight of the frame might have, obviously would have increased, and the necessary torque to rotate the frame would have been uh, uh, increasing as well.
Okay, sir, I got it. Thank you.
Okay, at this point, we can consider a single turn coil and try to write the expressions of the different torques associated with it, and later on try to develop a system level equation relating the deflecting torque in terms of the resulting deflection. So let's say if we have a single turn coil that is having a length of L, and from the rotational axis, from the central rotational axis, let's say the distance up to one edge of this coil arrangement is equal to R, and this coil is carrying a current, let's say in this direction, and the current is indicated by I. So this coil arrangement is placed in between a magnetic field. So some magnetic field lines are supposed to be there in between this uh, in between this single turn coil. So as here a motor action is taking place, let's say the current is flowing through the coil, and in presence of the magnetic field it is supposed to experience some force. So the Fleming's left hand rule can be used in this case. So if the Fleming's left hand rule is used, the direction of force would be in this way. So on this edge, considering the downwards direction of the current and the direction of the magnetic flux, the force would be on this direction, on this particular edge of the coil, and on the other edge, as the current direction is in the upwards direction, the direction of force would be along this line. So eventually, if this is the direction of current, the coil is supposed to have an anti-clockwise direction, in rotation in the anti-clockwise direction in this particular case. And for this particular edge, let's say if we consider this edge of the coil, then the torque, let's say at any one of the edges, the torque can be written as F T equals F into R. Now here, if B is indicating the magnetic flux density, then in terms of magnetic flux density, the current I and the length of the coil L, the force can be represented as B into I into L into R. So this is for one edge of the coil. Now the total deflecting total deflecting torque would be twice of what is written for as one single edge. So it would be twice B I L into R. And further, it can be written as Bi into A, where A is representing the effective area of the coil. So the length of the coil is L, and let's say if we consider the width, it would be actually twice R. So twice RL can be representing the effective area of the coil, and so we can write the deflecting torque to be Bi into A. Now this is for a single turn coil. Now a coil having n number of turns, the deflecting torque can be written as BIA into N, so multiplied by the number of turns of the coil. Now, apart from the deflecting torque, the coil arrangement is also going to experience some opposing torques. So one of the opposing torques is basically due to the springs. So the spring is going to cause some opposing torque to the coil arrangement. Other than that, it is also going to have or experience two other components of opposing torques. One is due to eddy current damping effect, and another is due to the inertial effect of the coil arrangement. So apart from the deflecting coil, the deflecting torque, three opposing torques are experienced by the coil. So at equilibrium point, when the coil is moving in a particular direction, then it becomes steady at a particular point. It can be said that at equilibrium, the deflecting torque is supposed to be equal to the summation of the three opposing torques. So at that point, the equilibrium will be reached and the coil or the pointer is going to be static or stable at a particular location. Now, among the three opposing torques, TC, that is representing the controlling torque, or that is normally known as the controlling torque, TB as damping torque, and Ti is the inertial torque. So we'll try to discuss a little bit more about these three torques and represent them in terms of the deflection. Let's say the deflection of the coil, we can denote it as theta. And we are going to try to represent these three opposing torques in terms of theta and some constants associated. So first of all, if we consider the controlling torque, as discussed, it is produced by the springs, and the resulting torque will depend on the spring constant of the particular spring. So like in case of linear motion, we can represent the force in terms of the linear displacement and the spring constant. So here in this case, we can say that the controlling torque will be proportional to the rotational displacement, and the proportionality constant in this case can be the spring constant K. So K here is representing the spring constant. So the controlling torque can be represented in terms of the deflection theta and the spring constant in this manner. Now the damping torque is generally due to the damping or opposing torque produced by the uh, uh, eddy currents induced in the coil arrangement. So the coil arrangement is going to rotate after it is carrying some current. So when the coil is carrying some current in presence of the magnetic field, it is going to experience some force. Now while it is moving or it starts moving, the moving coil inside the magnetic field will induce some electromotive force of its own. That is because some eddy currents will be induced inside the frame. So any moving conductor in presence of the magnetic field gets some eddy current induced that creates some uh, uh, that current creates some magnetic field of its own, and according to Lenz's law, that magnetic field actually opposes the main field. So this this phenomena will actually cause some weakening of the main field, and in a sense it can be said that it is causing some opposing torque that is causing or uh, uh, slowing down the deflection of the uh, entire coil arrangement. So this phenomena is often called eddy current damping. Now, from your control system course, you have an idea about uh, why the term damping is necessary, or what is it signifies. So, one of you can try to summarize that why damping is necessary in a system.
So to make it stable.
To make it stable, and I mean, yes, to uh, prevent the abrupt changes or oscillations. Some if some damping mechanism is there, then it will make the change in a particular uh, uh, response to be slow and smooth, rather than having abrupt changes that may result in oscillation. So this eddy current that is producing a magnetic field which opposes the main field, which eventually slows down the swing of the pointer, is actually introducing some sort of damping to the system. So this prevents the pointer to rotate at high speed whenever it experiences some deflecting torque. So in that sense, it is producing some damping or stability to the system. So this sort of torque is normally represented in terms of the damping constant d and uh, the rate of change of deflection. Now d here represents damping constant or damping coefficient. So the last one, which is the
Could
inertia
you
torque.
repeat the part? How are we getting the equation?
It is a general equation where the rate of change of deflection is related in terms of the damping constant. So the damping constant will here will depend on the uh, arrangement of the uh, uh, entire coil, along with the frame and uh, the number of turns and all uh, what is that, the iron core, the entire coil arrangement. So it depends on which type of material is used and how much uh, I mean opposing torque it can produce. So in terms of that, the damping torque is defined and or signified for a particular arrangement, and it is related or it is multiplied with the rate of change of deflection in order to determine the uh, damping torque. Now the last type of opposing torque is the inertia torque, and it is normally defined in terms of the moment of inertia and the angular acceleration of the particular coil movement. So it can be related in terms of the uh, what should I say, the distance that is covered into the circular trajectory. So if this is a circular trajectory that uh, might be covered by a particular coil arrangement, let's say a particular displacement of theta will result in a arc length of s into the circular periphery. So that arc length s can be represented as the multiplication of r into theta. So if that is the arc distance, then the velocity of this uh, movement can be considered as derivative of s, so which will eventually give us d theta by r into d theta by dt, and the angular acceleration then can be termed as the derivative of the velocity, which is r d square theta by dt square. Now, in case of force, we normally associate with it with linear motion, and torque in case of rotational. So, in case of force, we uh, know the general expression F equals ma, where the mass is related with the force in terms of the acceleration. Now, if we want to represent it in terms of torque, we can multiply both sides with the I mean, distance from the edge to the central point r, and later on we can also replace a with the expression of the angular displacement that is written over here. So it will give us mr square to d square theta by dt square, and this mr square is actually representing the moment of inertia j, and with respect to that, this particular expression can be obtained. Now, to write the system level equation now, the deflecting torque Td can now be written in the form of a second order equation as this one. So it is relating the deflecting torque with the deflection theta in terms of the second order equation associated with the constants, the moment of inertia, the damping constant, and the spring constant. So in order to examine the behavior of the uh, system, this second order equation can be considered, and it can be solved as an homogeneous equation or developing an auxiliary equation considering this second order differential equation. The roots of the equation can be the expression for the roots can be written. So if we write an auxiliary equation with respect to theta, so let's say we are going to represent the equation in terms of m. So if we have derivative terms, that is a second derivative, we can represent it as jm square plus d into m plus k into 1 equals 0. So let me write it like this, keep it like this. Now this represents the same equation in terms of a second order uh, uh, a quadratic equation. So the general method for the known formula for determining the roots can be used, that is minus d plus minus root over b square minus 4 into k into j divided by twice j. Now if the roots are known, let's say two roots are going to be obtained, m1 and m2, then the solution of the system can be written in terms of, let's say, two constants c1 e to the power m1x or plus c2 e to the power m2x. So some in this way or another, I don't entirely remember. Maybe if you have studied this in your control system course this semester, I think you remember better than me. But once you have the roots of the auxiliary equation, you have this sort of a format where you can utilize the roots of the auxiliary equation in determining the solutions. Now you can check it out later on that how to do that, but from these roots of the auxiliary equation we can characterize the nature of the or behavior of the system. So we can consider three cases for the time being. So case one, where we can consider if what would happen if d square is less than 4 into k into j. So if that is the case, then you can say that the roots are going to be complex in nature. So if the roots are complex in nature, and they are going to be in the left half of the S-plane, but as they are complex, you can say that the condition that you are going to obtain is going to be an underdamped condition. And it is if it is an underdamped condition, there would be some amount of oscillation in the motion of the pointer before it reaches the steady state condition. Now if case 2 is considered, then there we can say that if d, what would happen if d square is equals to 4 into k into j. Then in this case the roots are going to be real and equal, and if this particular condition arises, then you can say your system would be critically damped. And if it is critically damped, then the system will gradually reach the steady state point, and the system can be termed to be a non-oscillatory system. And the third case, where d square can be greater than 4 into k into j. So in this case, still the roots are going to be real, but they are going to be unequal, and that will result in a overdamped situation. The system will be non-oscillatory, but the response will be slower compared to the critically damped case. So it will take more time to reach the steady state point, or the settling time will be more in this case. So in terms of diagram, this could be uh, uh, step response in terms of the deflection of the coil. So the underdamped case which satisfies this particular condition can be represented by this curve, where there is some oscillations before it reaches the steady state point. The critically damped case, which is reaching the steady state point without the oscillations of the overshoot at rather a quick pace, and the overdamped case, that is reaching the steady state without oscillations, but uh, with having a larger duration, larger time. So in this way, depending upon the damping coefficient and the spring constant, or the moment of inertia, the nature of what would be the nature of behavior of the system, that can be uh, predicted if these values are known, or if it is possible for the manufacturer can try to control the uh, or design the structure in such a way that his desired condition is satisfied, that the condition that the manufacturer wants the system to operate in. So if that can be ensured, then the manufacturer can ensure whether in which condition the manufacturer wants the moving mechanism to operate. Now, some sources of error for this type of moving mechanism could be in terms of weakening of the magnets, the permanent magnets, due to aging. If they are used for a long time, their magnetism is supposed to be decreasing. So that could be one of the sources of error. And also the weakening of the springs uh, due to aging can be another source of error when these sort of devices are used for a longer duration. So if the springs are weakening due to the aging effect, maybe they would not be able to bring back the pointer back to zero as it's supposed to be. So there might be some mechanical errors in those cases that might be introduced. And also the change in the coil resistance with change in temperature, if that is significant, that can also cause a possible source of error, because if the resistance of the coil changes, the amount of current is going to carry will also change for a specific supply. So that could also introduce some source of error. Now, among some of the advantages of this sort of moving mechanism, the uniform scale that can be used along with the movement can be considered to be one of the advantages. Then this sort of mechanisms can operate with lower power consumption than the uh, uh, generation of eddy currents that is producing some sort of damping to the system. That can also be termed as one of the advantages of this sort of moving mechanism. Now, Up to this, I wanted to discuss in today's class. Now, in the next class, we can, or in the next lecture, we can discuss about uh, how this moving mechanism can be incorporated in uh, forming ammeters or voltmeters, or uh, how this mechanism was further modified in order to form the electrodynamic meter movement. So in the later lectures, we are going to try to discuss about those. So now, anything from your side? Otherwise, we can conclude today's session up to this. Okay, as you're not responding anything, I'll conclude today's session here. But before that, I should inform you about that next week we were also supposed to have two classes. Now, the exam for this course is set on 12th, the final exam.
Yes, sir, it's on 12th.
So considering that, I'll try to upload pre-recorded lectures about the remaining topics that were supposed to be discussed. Maybe I'll not take the classes on next week, but within this week, I'll try to upload all the recorded lectures regarding the topics that were supposed to be discussed, as this is the first exam, so that you can use the next week for your preparation purpose. So uh, the remaining lectures, I will try to provide you recorded videos within this week, and you can look into the Google Drive folder for those.
That will be very helpful, sir. Thank you.
Sir, what will be the topic for the next quiz?
Oh, for the next quiz, the topic would be the discussion done on PLC. So it is scheduled on 9th of January. So the time I'll later on fix with the seer, but the topic would be regarding the lecture on PLC. So you can follow that slide and the related videos and take preparation for that as well. And I think 9th is a Saturday, so we can have the exam at, if it is a Saturday, we can have it on 2:30. Yes, it is a Saturday, so we tentatively we may have the quiz on 2:30, but I will confirm with the seer later on.